Okay, so in this video, we are going to discuss moment of inertia. So, as we know that there is angular velocity, and this is analog for linear velocity in case of rotational motion. And then we have torque, which is analog for force in case of rotational motion. And we have, of course, angular acceleration as well. And this is analog for linear acceleration, or simply we write it acceleration. Okay, so if we observe these equations, F equals to ma, or linear momentum equals to mass times velocity, then we can say that this torque should be somehow related to this angular acceleration. And here there should be a term which is rotational analog for mass. And of course, if we are saying angular momentum, so here we have angular velocity, and there should be a term, the same term, that is rotational analog for mass. So there is such a term which we call moment of inertia. Moment of inertia. So whatever mass plays role in case of linear motion, moment of inertia plays the same kind of role in rotational motion here. So let us move further. Okay, let us try to find out what could be its expression. So we know that in case of rigid body, which is being rotated here, and let's consider it is made up of n number of particles. So let's say we have chosen a random particle here, and it has mass mi, ith particle, and this, while this body rotates about this axis, this mass will cover a circular path around this axis. And let's say its distance, this perpendicular distance, is represented as Ri. So the moment of inertia, okay, we will come to that point. So it has kinetic energy. This rigid body has kinetic energy, and this body is moving. It has also kinetic energy. So we can write that kinetic energy for this ith particle will be 1 by 2 mi and vi, if its velocity is linear velocity is vi. So this will be its kinetic energy square of this term. Okay. If we want to know what is the sum of all these kinetic energies, means if we are choosing all the particles from first to nth particles, as I said, this system is made up of n number of particles. So if we want to know what is the sum of all those kinetic energies, so we can write that total kinetic energy, let's say it is Ke simply, will be of this system. So let me write it Ke of system. It will be summation over I equals to 1 to n and mi vi square. Okay. Now, as we know, look, this is perpendicular to v. If I am saying this distance, this is Ri, this is perpendicular to v, because this is kind of radius of this circular path, and velocity is always tangential. So this distance or this length will be perpendicular to v. In that case, we have magnitude of this linear velocity r into omega. It will be r omega sine 90 degrees. So ultimately it will be r times omega. Or you can take vector things too. So you can take vi equals to ri cross omega I. So this will be Ri omega and sine 90 degree, and there will be something n cap, which is along this velocity vector. Okay. So this is what we are going to get here. And here instead of velocity, it is squared. So a square of any vector is going to be a dot product of the vector with itself. So as we have done already, that if we want to know what is A dot A, this is going to give us a square of magnitude of this vector A. Otherwise, cross product is not going to give us a square of magnitude. So ultimately, we will have here I equals to 1 to n. This is equality sign 1 to n and mi, and then we will have here ri square omega I square. Okay. If this is rigid body, if this is rigid body, that is, it is going to complete one rotation in the same time as each and every particles are going to complete one rotation. So angular velocity for each and every particle in this rigid body will be same because they are all going to complete one rotation or revolution in case of particles, one revolution about this axis in same time. So this angular velocity will be same for each and every particle. Otherwise, this body won't be rigid anymore if they are lagging or leading to one another. So I equals to 1 to n m I r I square and omega square. So I'm missing here 1 by 2. So this is 1 by 2, 1 by 2. Now we can compare because this body, if we are taking this body as a whole, so this body has no translational motion at all. Even particles are moving on certain path, they have a kind of translational motion, but this body as a system has no translational motion at all. So we can say that the kinetic energy possessed by this body is due to its rotation, or we can say it is kind of rotational kinetic energy. In that case, we will have kinetic energy of this system equals to 1 by 2, and here we have something mi ri square and then omega square. Look, we have arrived at a situation where we can compare a general formula kinetic energy equals to 1 by 2 mv square in case of linear. Here, rotational motion, we have angular velocity square, which is resembling this velocity square, and here we have a term which is resembling mass. As the mass functions in case of linear motion, this term is coming in case of rotational motion. And this is what moment of inertia for this system of particles. So I can write moment of inertia for this system is sum of I equals to 1 to n mi ri square. Okay. Now you can find out its SI unit as well as its dimensional formula. So SI unit should be, if we are taking this is mass, this is length, SI unit should be kg meter square, and its dimensional formula will be this is for mass and this is for length. Okay. Now coming back to the earlier discussion here. So now we know that here we have a term which is angular motion analog for mass. So, and what we are representing moment of inertia here by I. Okay then. So we have these two things now, and of course there will be many more coming. Okay, coming back to this point now. So this is for a system of particles where there are n number of particles. Let us start from a single particle. Let's say we have, I'm writing here for single particle. Now we are going to obtain moment of inertia for different systems. So starting from very basic, let's say this is axis of rotation, and about this there is a particle of mass small m, and its perpendicular distance is small r. It is moving on a circular path of radius r. So its moment of inertia this about this axis will be mass times r square. Okay, let's say we have two particles. Then the moment of inertia, let's say we have one particle here at distance r1 and its mass is m1, and there is another particle here at distance, this is axis of rotation, m2, and its distance is r2. So we have I equals to m1 r1 plus m2 r2. squared of these two things. MRS M1 R1 square and M2 R2 square. And here now I would like to make some comments on this moment of inertia. So look, this moment of inertia depends on, first, this is depending on mass. So mass. Second, position means its distance from the axis of rotation. So we can write it. Let me write it position only. Then, as this position is depending on axis of rotation, so this will be depending on choice of axis. And as it is depending on this position, it is also going to depend on this mass distribution, how these masses are being distributed. So, of course, mass distribution. Now we have reached in a system of particles after making this comment. So, if we have a rigid body or simply an extended body, so shape and size is also going to play a role in this moment of inertia, and mass distribution we have already discussed here. Now I am going to introduce one topic here, and thereafter we will continue this discussion in the next video. There we will try to obtain moment of inertia for various regular shaped objects, obviously. So now I'm going to introduce a term called radius of gyration. Okay, what does it mean? Let's say we have a system of particles where there are n number of particles and a kind of extended body, we can say a rigid body, and n number of particles are constituting this rigid body.